You may not believe it. Although gravity rules the universe, but compared to several other fundamental forces in nature, it's simply weak. The quality of our planet is 5.97 times 10 by 24 power of the kilogram. That's a big number. But even so, the gravitational pull generated by the Earth is still weak. So much so that you pick up a cup of coffee every time, or get up from your chair, can easily defeat this force. This shows that you are really powerful. As an ordinary human being, it can actually be hard head-on. The force that makes the moon revolve around the Earth. Speaking of the moon, although it is much smaller than Earth, but the impact on us is amazing, large enough to push the whole seawater, creates tidal phenomena, the rise and fall of the COC by the sea. In fact, it is between the gravity of the Earth and the gravity of the moon, the results of a subtle dance. But this brings up an interesting paradox. Gravitation, how can it be so weak that you can make a random move? Can be overcome. It is strong enough to make planets revolve around the sun. You can also organize an entire galaxy. It's just one of the many fascinating properties of gravity. To truly understand how special gravity is, we have to compare it with the other three fundamental forces of nature. Put them together and compare. That is the electromagnetic force and the weak nuclear force. There is also a strong nuclear force. To be honest, many physicists, not even really, gravity is classified as the same as several other forces. As for why, we'll talk about this later. Let's talk about the strength of these four forces first. The champion has a strong core. He is responsible for putting protons and neutrons firmly stuck in the nucleus. This is actually quite incredible, because protons are inherently mutually exclusive. After all, they all carry a positive charge. The same charge is to be repelled, but the nuclear power is too strong. It just overwhelmed this electromagnetic repulsion, bringing everything together. In terms of strength, the strong nuclear force is about 10 times the power of 38 of gravity. This number is too large to imagine. We do not feel its presence in everyday life. The only reason is, it only works at extremely small distances. This is a distance smaller than the nucleus. After a strong nuclear force, there is a weak nuclear force. Don't be fooled by this name. Although the name is weak, but compared to gravity, it's boundless. It is this force. It dominates phenomena such as radioactive decay. This is a crucial factor in nuclear physics, and the energy that drives the star are crucial. If there is no weak nuclear force, the sun does not shine at all. Ultimately, it is the weak nuclear force that makes the hydrogen in the core of the sun, transforms into helium, releases light and heat. This force, it is transmitted by particles such as W-wave protons and Z-wave protons. The distance of action is smaller than that of the nucleus, although it is about 1,000,000 times weaker than a strong nuclear force. But it is still 10 times stronger than gravity to the power of 25. Even on such a microscopic scale, its importance to the operation of the universe should not be underestimated. Next, it's time to talk about the forces that govern our daily lives. That is electromagnetic force. Today we can have electric light computers, and almost all modern technology. It's all because we've learned to harness this force. It is closely related to the properties of electrons. It is transmitted by particles such as photons. Every time you press the switch, or see the compass pointing to the Earth's magnetic field, you're witnessing the action of electromagnetic force. Although it is weaker than strong nuclear, but electromagnetic force has a special place. It can act over long distances. It's like gravity. This property allows it to shape not only atoms and molecules, it can also affect phenomena that we perceive directly. and in strength, it is 10 times stronger than gravity to the power of 36. Another astronomical number. I want to see how much it has a scope of effect. Just look at the ordinary compass. A small piece of metal is able to respond to the magnetic field of the entire Earth. This shows that the electromagnetic force is sensitive. It can cover an astonishing range. Now we know how weak gravity is compared to other forces. But he is actually the architect of the universe. If there is no gravity, there would be no galaxies, stars, and planets, not to mention life. The whole universe will be a chaotic void. Scattered particles floated everywhere. There is no structure to speak of. The key to all this is time. Gravity is like a patient craftsman who never tires. He doesn't need to be strong. As long as the work continues for billions of years, can turn chaos into order. Isolated particles begin to attract each other. Small clumps are formed. These clumps add mass, make local gravity stronger, and then it attracts more substances. This cycle repeats for 13.8 billion years. It made up everything we see today: stars, planets, solar systems, and entire galaxies. And the process is not over yet. The formation of the universe continues now. Just as you came across this video, stars are being born. Galaxies are merging. Gravity is still there, shaping the universe with its near-infinite patience. Many people think gravity is just what we feel on Earth, that invisible force. But its imprint is actually all over the universe. It exists in the cradle of the star. There the gas cloud contracts to form new stars. It exists in black holes. There it was so powerful that even the light could not escape. It defines the shape of the spiral galaxy, keep the planets in stable orbits. And there's something even more magical. Just like electromagnetic force, the scope of gravity is unlimited. No matter how far away, gravity is still at work there, even if it is so faint that it is almost imperceptible. You must have heard of it. The classic line from Star Wars. A Jedi Master described the Force as an energy field created by all living things. He surrounded us, infiltrated us, connecting the entire galaxy. If you put all living things, replace with all objects with mass, this description is simply a perfect portrayal of gravity. Just like the Force of the Jedi, gravity is also everywhere, wrapped in everything. It connects the entire universe. Moreover, its scope of action is indeed theoretically limitless. This means any object with mass, from a grain of sand to an entire galaxy, will affect all other objects in the universe. Apply gravitational influence. Of course, this does not mean that you can feel billions of light years away the gravitational pull of a star. The key is as the distance increases, this force will become weaker and weaker. Nevertheless, there is a gravitational connection between all things. This idea is even almost imperceptible. It's really amazing. Although the scope of action is theoretically unlimited, but gravity does not travel instantaneously. For example, he can't run faster than light. The sun's rays and his gravitational influence. It takes about 8 minutes to reach Earth. This means if the sun suddenly disappears, we won't notice it until 8 minutes later. His light and gravity are gone. In addition, gravity follows the so-called inverse square law. This means that the force decays with the square of the distance. Translated into human words, if you are at a distance from a large mass object, double H, its gravitational attraction to you will be reduced to 1/4. The distance becomes 3 times. Gravity becomes 1/9, and so on. So although gravity never really goes to 0, but at a great distance, it will become too weak. So much so that it is negligible. This is why a certain area is inqualitative. the largest celestial body, for example, giant stars or black holes, will dominate the surrounding environment, even if there are many other small celestial bodies nearby. Now you are definitely thinking, what about my own gravity? I will not affect the people around me. Technically, yes. Anything with mass creates a gravitational field, including you, but actually, this effect is so small that it is almost impossible to measure. Let's do a quick math. Imagine two people weighing 100 kilograms each standing side by side. The gravitational force between them is only about 0.000411713 newtons. This number is small enough to be in everyday life, completely negligible. If you double the distance between them, this value will drop to 1/4. Other words, the gravitational pull your body exerts on another person, compared to the forces that truly shape the universe, basically equal to 0. Up to now, we see gravity strangely, but be prepared. Start here. He will become utterly weird. There is an effect. It is experienced by all objects with mass, including you. You just didn't notice it. That is the time dilation effect. A real existence is predicted by modern physics, but a phenomenon that is often misunderstood. In practice, this means time is not lost equally for everyone. Depends on where you are and how fast you move. The second hand may be elongated or shortened. This is particularly counterintuitive. That, when you really understand what's going on, you will realize, take time, measure as something absolute and universal. This matter doesn't make sense at all. Einstein's general theory of relativity explains, you are away from large masses. For example, the closer a planet or star is, the slower time passes. This is because gravity bends space-time, and the clock includes the biological clock of each of us. It will beat at a different rhythm. It depends on where they are, this position in the gravitational field. In fact, the closer you are to the center of the Earth, the slower time passes for you. The farther you go, for example, at the top of the mountain, the faster time flies. The difference is very small, but it really exists. For example, for every kilometer you climb, your clock is within 24 hours. It will travel about 10 nanoseconds longer than the clock at sea level. That doesn't sound like much, but enough for scientists to have to be in high-precision systems. Modify this effect. For example, GPS works fine. It is because these time changes are taken into account. And an interesting detail, the Earth is not completely uniform. This planet has different densities and irregularities. This means gravity can change slightly depending on where you are. Theoretically, each of us experiences a slightly different time. But the story is not over. Except for gravity, speed also affects the rhythm of the passage of time. This is Einstein's special theory of relativity. A fascinating example comes from the International Space Station. At first glance, you might think, the astronauts are at an altitude of about 400 kilometers. The Earth's gravity is slightly weaker there. The time they experience, it should be faster than the people on our ground. But quite the opposite. The International Space Station is amazing. Fly at a speed of 7,700 meters per second. Relative to Earth, it is about 27,600 kilometers per hour. The time dilation effect produced by this velocity surpasses their advantage in staying away from gravity. As a result, the time there is a little slower than ours. As a matter of fact, an astronaut who has been on the space station for 6 months, when you return to Earth, lived about 0.007 seconds less than staying on Earth. This effect is small, but it's completely true, and it has been measured with high accuracy. At this point, we are talking about a change of time. It was so small that it seemed insignificant. But here's the point. They do exist. And when something exists, it could accumulate over billions of years. A stunning example is the Earth's core. Because closer to the center of the Earth's mass, time passes a little slower there than on the surface. The result was 4.5 billion years. The Earth's core is larger than our crust, about 2.5 years younger. It has little impact on our lives, but it reveals how real and measurable gravitational time dilation is. That's it. We have always regarded gravity as a force. It seems that it is similar to electromagnetic force or resultant force. But the truth is, it shouldn't be classified with them at all. Gravity, as we understand it today, it is actually the result of the curvature of space-time. Imagine the universe as a big stretchy cloth. Put a mass object, for example, planets or stars. The cloth will be deformed. Other objects nearby eventually fall into this depression, not because something is pulling them. It's because of the space they move. It is curved in itself. That famous metal ball, the metaphor of pressing on an elastic bed, helps to imagine this. The ball represents the Earth. The bed represents time and space. But it's not just a flat depression. What really happens is a complete three-dimensional distortion. It is as if the space is shaped around the mass. This image helps to understand why gravity is so different from other fundamental forces. One of the most fascinating aspects of this twist is it affects not only massive objects, it also affects light that has no quality at all. Usually light travels in a straight line, unless it encounters a physical medium like water or a lens, leads to refraction. But in the case of gravity, there is no medium at all. What has changed is space-time itself. Light in this curved space followed the straightest possible path. This is what we see. It rises like a curve. This phenomenon is known as gravitational lensing. It is Einstein's theory, one of the most impressive pieces of evidence. Precisely because of it, astronomers can observe extremely distant galaxies, use galaxy clusters as a true cosmic lens. And when we stop to think, something that bends the light, it is not a force at all in the traditional sense. It is a feature of the geometry of the universe itself. At this time, our brains may not be enough. If you want to see the bending of light on Earth, I'm afraid I'm going to be disappointed. The gravitational effect of our planet on light is too small. It is not noticeable at all. But the good news is, this phenomenon is observable. Merely, we need to look at objects with much greater mass. You also have to use a powerful telescope. When a huge mass concentration, for example, a galaxy or galaxy cluster, when it is located between a distant light source and us, its gravitational pull can distort the spacetime around it. The result is, light from distant sources bypasses this mass, reach our eyes. It looks like it's coming from several directions, forms distorted images, even a perfect aura. It's like the universe itself, focusing light with a huge lens. These effects are not just good-looking. They are also a super powerful tool for astronomers. Through a gravitational lens, we are able to study extremely distant galaxies, detect dark matter that does not emit light but distorts space. It can also study how the universe expands. But no matter how amazing the gravitational lens is, compare it to what happens in a black hole. It was still too gentle. That's where gravity reaches its most extreme state. You often hear that even light cannot escape a black hole. Now you understand why. The curvature of spacetime there is so deep, so much so that there is no escape from the incident. There is absolutely nothing inside the world that can run out, not even photons traveling at the speed of light. what will happen to the light and everything that falls into it, remains one of the biggest puzzles in physics. Time and space are distorted too much. Our equations are no longer reliable. Even the best theoretical models. It's also hard to describe what happened beyond this invisible border. And that brings us to one. Even the smartest brains on Earth will be confused. The boundaries of gravity and quantum physics. Until now, we are talking about gravity. It's all just as Einstein described. A smooth and elegant bend of time and space. He perfectly explains large-scale phenomena. For example, planets, stars, or entire galaxies. But when we try to apply the same logic, when applied to the subatomic world, everything started to fall apart. 3 basic forces: electromagnetic force, weak nuclear power, and strong nuclear force, works very well at the quantum level. Each of them has a specific particle delivery. Photons transmit electromagnetic forces. WNZ wave photosomes transmit weak forces. The gluon transmits strength. These messenger particles. Let's use field and energy quantums to describe it. These forces are a bit complicated, but logically self-consistent. But gravity doesn't work. We have never found a medium particle for gravity. This particle, until now, it is an imaginary graviton. Even if it exists, describing it also requires quantizing spacetime itself. And this is something we still don't know how to do, without producing absurd and contradictory things. As a matter of fact, when we try to explain the macroscopic general theory of relativity and explaining the microscopic quantum mechanics, our mathematical equations fall into paradoxes. It's like two fundamental parts of physics. It simply cannot be put together. For those who seek the theory of the unity of the universe, this is obviously a huge problem. So the true nature of gravity at the quantum level remains one of the biggest mysteries of science today. But that doesn't mean scientists are sitting idly by. Contrary, there are teams all over the world trying to solve this puzzle. Some of the most discussed hypotheses, including imaginary particles such as gravitons. It will be a messenger of gravity, just like photons due to electromagnetic force. If this hypothesis is confirmed, this discovery, it may bring gravity in line with other fundamental forces. It can greatly simplify our understanding. The problem is so far, there is no experimental evidence of the existence of gravitons yet. There is also string theory. He proposed everything in the universe, including particles and forces, are all caused by dimensions outside of our perception. In the extra dimension, it is composed of tiny strings that vibrate. There is also a circle of quantum. The theory of gravity attempts to quantize spacetime itself. It is proposed that it consists of discrete structures, almost like the pixels of the universe. Although these theories are fascinating, but they are still highly speculative, far from reaching a consensus. None of them can be conclusively confirmed. A question that is being discussed more and more at the moment is, what if gravity cannot be quantized at all? Some physicists believe perhaps it is necessary to create a completely new model of reality. One combines the quantum world and classical time and space, combined into a model of something we don't know at all. One of the researchers in this area is Jonathan Oppenheim of University College London. He believed that the next great revolution in physics would be probably from a kind of neither quantization nor completeness. It is also a completely canonized theory. Rather, it is a mixture of two world aspects. Only a slight modification of quantum theory is required. Slightly modify the generalized relative theory can unify the two. Although his ideas are still controversial, it was also not widely accepted. But they point to an important fact. Current physics, a radical update may be needed to explain gravity at all scales. So gravity is far from as simple as an apple falling. It is still a great intellectual challenge. It can frustrate generations of physicists. But it is this exploration that drives science forward. Every hypothesis, every bold theory, every new experiment, all bring us closer to understanding reality in essence.